Curiosity may or may not have killed the cat, but we're not in physics. This is my AP Chem video, and don't look outside the window because there might be monsters. So what is chemical equilibrium? You do know what a chemical reaction is, right?
No.
Well, we all know the 7th grade textbook definition of a chemical change. A chemical change, unlike a physical change, is something that can't be undone. So the same must be true for a chemical reaction, right?
Right.
Wrong.
In most reactions, there is both a forward and a reverse reaction. Chemical equilibrium is a state at which the forward reaction happens at the same rate as the reverse reaction. This means that once the reaction reaches equilibrium, even though the reaction is still taking place, there is no net reaction, and the amount of product and reactant is constant. Now that our example has reached its pretend equilibrium, the same amount of water is being moved both ways, even though I'm using two different sized cups. This is just like how the rate of a forward and reverse reaction become the same when they did not necessarily begin that way.
And there is your equilibrium expression.
A saturated solution is a solution in which the maximum concentration of solute has been reached. A solution that is at equilibrium with undissolved solute is said to be saturated. One example of a saturated solution is the green water from earlier. Before extra water was added, the concentration of food dye in the water was too high, so the solution became saturated and the dye did not dissolve all the way. An endothermic reaction is a reaction in which heat energy is used up to move the reaction forward. An exothermic reaction is a reaction in which heat energy is given off as a product of the reaction. Here is a tub of apple cider vinegar. Of course, everyone knows the baking soda volcano. But did you know that this reaction is actually endothermic? I guess volcanoes aren't as hot as they used to be. Note that the initial temperature was slightly above 70 degrees Fahrenheit. The fact that this reaction is endothermic means that in order for it to move forward, heat energy must be used up. So what does that mean for us? This causes the temperature to feel colder. When we measure the temperature after the reaction has taken place, we can see that it has dropped to just above 60 degrees Fahrenheit. That's almost a 10-degree drop from the original temperature. Solubility is a chemical property referring to the ability for the solute to dissolve in a solvent. It is measured in terms of the maximum amount of solute dissolved in a solvent at equilibrium. The molar solubility of a substance is the number of moles per liter that dissolve in a solution. Molar solubility changes. The solubility product constant, or KSP, does not change unless the temperature changes. Having a common ion means that there are already ions in solution that are part of the equilibrium expression. This causes molar solubility to decrease. In this example, we have the dissociation of barium sulfate. Let's assume we have 0.1 molar sulfate ions already in solution. When we write our ice table, the initial concentration of sulfate will be 0.1 molar instead of 0. We know that the KSP for this reaction is 1.1 times 10 to the negative 10th, so we can set that equal to the equation. So, 1.1 times 10 to the negative 10th is equal to x times 0.1 plus x. According to the 5% rule, because the value of x is so much less than 0.1, it can be disregarded. This is like how in math anything added to infinity is insignificant. We then solve for x and end up with 1.1 times 10 to the negative 9th. Now, let's solve for x assuming there is no common ion already in solution. We will set up the ice table the exact same way as before, except with the initial sulfate concentration of 0. The equation becomes 1.1 times 10 to the negative 10th equals x squared. X comes out to be 1.0 times 10 to the negative 5th. Now we can truly see the effect of a common ion. Even a small amount can have a big effect on molar solubility. One thing that can affect solubility is heat. Here we have 2 different cups with the same amount of instant coffee in each. To the first cup, I add hot water, and to the second, I add an equal amount of cold water. Then stir both to ensure maximum dissolving capability. Even with a decent amount of stirring, you can see that there are still chunks left undissolved from the cold water. Even when all of the liquid coffee was poured out, there was still plenty of solid bits left in the cup with cold water. There were none left in the cup with hot water.
According to this nifty chemistry terminology guide I got at St. Norbert College in Wisconsin, Le Chatelier's principle states that equilibrium shifts in response to changes in conditions. This means that by messing with the reaction, you can move it to the left or to the right to make more products or more reactants. It's all about balance. Le Chatelier's principle can be explained using one of my favorite topics, music.
In music, there is a rule that dynamics are relative. Say there is a flute and a trumpet playing a duet. In this reaction, the flute and trumpet air are aqueous reactants, and the amount of sound you hear is the gaseous product that fills all of the space it's given. Now suppose we give more air to the trumpet. The sound becomes bigger, which pushes the flute to use all of his remaining air. Because more air is being used, a bigger sound is produced in order to keep the balance. Word!
Le Chatelier's principle can be found in many of the examples we have seen today, just like in the baking soda vinegar reaction. As excess baking soda was added, it shifted the reaction to the right until all of the vinegar was used up. The coffee had a different type of excess, but the result was still the same. The excess heat caused the reaction to move to the right and the coffee to become more soluble.
I've been the cat, not in a hat, and these are my favorite people.